The next topic is electromagnetic and mechanical forces in power transformer. So until now we have seen the leakage reactance. So it is the next topic. Introduction. Failure in a power transformer is almost always attributed to a mechanical damage of the oil impregnated kraft paper insulation. The electromagnetic forces arising out of the interaction of the winding currents and the magnetic flux are the cause of these failures. The most severe mechanical stressing occurs in a transformer when it is subjected to a sudden short circuit due to the enormous magnitude of the currents leading to abnormally high forces. So you can see the adjacent figure here. So in this figure, you can see the damaged portion, you can see here. So the reason for failure of a power transformer is due to mechanical damage. Mechanical damage actually, as already studied in one of the classes, previous classes, the failure, the aging of the material, this is oil impregnated paper actually inside. So paper based insulation mostly. So since oil is impregnated, its dielectric strength lasts for a long time until it is mechanically damaged. The dielectric strength remains. So then how the mechanical? So the moment the mechanical strength is lost, and any sudden instance like short circuit will cause heavy forces, and then that will crush the insulation, and then that will lead to the failure of the insulation. So as long as mechanical strength is there, the transformer is safe. If the mechanical strength is lost, then immediately any force like short circuit force, currents, etc., will cause it to fail. That is the main mode of failure of a transformer. Although the windings are designed to withstand short circuit forces, so small duration, although the windings are, just wait, why these are coming. Although the windings are designed to withstand the short circuit forces, for a small duration, the effect of factors such as aging and frequent and prolonged overloading, etc., leads to a reduction in the withstand capability over a period of time. Yes. So as discussed in earlier lecture, the dielectric strength of the oil impregnated kraft paper remains intact for a long time due to the oil impregnation and barrier effect, even as the mechanical strength falls drastically. So the moment the mechanical strength is completely lost, then any force will cause it to crush, and then the failure occurs. Thus an accurate estimation of electromagnetic forces acting on the windings is necessary for a good design as well as condition monitoring of the power transformer. Now, origin of the forces. From the basic electromagnetic theory, we may recall that every current carrying conductor placed in a magnetic field experiences a force. F is equal to BIL, you may be remembering, Bill. So this is dF, differential force acting on a current carrying conductor of differential length dl carrying a current I in a magnetic field density B. So IDL cross B is the differential force, and then the total force is total length of the conductor B, L cross B into I equals to F. Since the resultant force is cross product of then directed current segment and the magnetic field flux density, the force is perpendicular to the direction of current as well as the direction of magnetic field. That we know from fundamentals of electromagnetic theory. Then alternatively, the force acting on a conductor may be described in terms of the associated energy. So this is what we will use in this actually. So a force is obtained how? From the energy we will see. E equals to P into dt, integral power into time, and then that can be replaced by F dot V into dt or F dx by dt into dt until 0 to 2, integrated 0 to t, and dt can be cancelled out. This is integral of 0 to x f dot dx. Now, if you differentiate this is integral form. If you differentiate, you will get f equals to dE by dou E by dou x. Of course, modulus of f equals to dou E by dou x. Then taking differentiation on both sides, you will get where the symbols have their usual meaning. Okay, the force direction is opposite to the movement of this dou x, that we may remember. So this is how by differentiating the energy we will obtain the force. This concept is used in this to understand forces acting in the transformer. So forces in a power transformer. In a power transformer, the flow of winding currents lead to development of a magnetic flux which has two components, the mutual flux and the leakage flux, but which is important. So as discussed in the previous lecture, due to actually this mutual flux is within the core only. So forces on the windings are mainly due to leakage flux. As discussed in the due to high reluctance of the air and the windings, both of which are non-magnetic media, as opposed to low reluctance of the transformer core, the energy associated with the establishment of the leakage flux is more compared to that associated with the main flux. Hence, the electromagnetic forces resulting out of the interaction of the winding currents with the leakage flux density are predominant, since as seen in the previous slide, the force and energy are directly related. So forces in a power transformer. So the distribution of leakage flux as discussed is predominantly axial along the height of the windings, as already discussed in one of the previous classes, but changes to radial towards the ends. So you can see at this end portion, it tends to be radial, and here in the main height of the portion, this is the flux lines are simply axial, parallel and axial. So where the flux lines tend to be. According to the sake, for the sake of analysis, the forces produced by the axial and radial components of leakage flux are separately treated. Due to the force being perpendicular to the flux density vector, it is therefore evident that the interaction of the current with axial component of the leakage flux leads to radial forces, and that with the radial component of the flux leads to axial forces. This is how. This is due to the direction of the force. Just now we have discussed in the electromagnetic force, the direction. So radial forces. Now let us go through the radial. The calculation of radial forces is relatively simple, owing to the fact that the axial component of the leakage flux is well defined. The nature of the radial forces is such that they tend to crush the inner winding against the core and burst the outer winding. So this is how it is actually. They tend to crush it because this is the, if you look from the top, this is like this, right? So all forces will be like this for the inner winding. So inner winding, it is crushing forces, you can say. And for the outer winding, by this direction actually, if you consider these are the conductors having, dot means the currents coming out, and these are the conductors, currents going in. So it is, if you assume the forces between these two types of conductors, then the force will be like this, right? They will be repelling each other, in other words. So the overall force also will be like this. On the inner winding, this is the inner winding width you can take. This is the inner winding width. Inner winding, and this is outer winding. On outer winding, the forces will be like this again. So a big circle I have to draw. So this is bursting force, right? So this is the bursting force. So in other words, the radial forces act as a compressive force on the inner winding and a tensile force on the outer winding, or bursting force, you can say. Assuming the windings to be rigid bodies, the forces are uniformly distributed throughout the body. So if they are rigid bodies, then obviously that is uniformly distributed. Radial forces are uniformly distributed. Yeah, here it is given. So this is central portion. The central portion is core actually. This is core diameter. So this is the top view, you can say. And then, okay, I'll write like this is core. Now, this is inner winding. This is outer winding. You can see the forces acting. On the inner winding, the forces will be, like this, crushing forces. On the outer winding, they are bursting forces outward, like this. Already these black arrows indicate the forces. These forces, the total force Fr, total radial force outward, bursting force must be equal to the inward force Fr, compressing force, equivalent opposite. So for the given winding configuration, the expression for energy associated with the leakage flux, in our previous lecture we have seen, the energy associated with the leakage flux, total energy, this is total energy, is given by half mu naught into n square I square by HR pi d W1 by 3 plus W2 by 3 plus Wg. So if allowed to act independently, the radial forces will tend to induce a displacement, thereby changing the air gap with the Wg. Suppose if they can move, a little, if they can move, then the Wg can be altered. So it must be differentiated with Wg. That x, dE by dx, dou E by dou x is there. That x is dou E by dou Wg here. Thus, to calculate these forces, we have to differentiate the energy with respect to the radial distance Wg. So, the force, total radial force, because this total energy is dou E by dou Wg. Dou x, you have seen a few slides before, that is here the dou Wg, because this is the only distance which can alter, assuming that these are rigid bodies, and then this width etc. doesn't change, W1, W2, and so Wg will be tend to alter Wg. So therefore the radial force is dou E by dou Wg. Thus the radial force may be expressed as, yes, this way, and if you differentiate that, you will get half mu naught n square I square by HR into pi d. So if you separate it out into 3 different parts, you can see this portion is mu into h. Mu into h means B. And this portion Ni is simply I current. and this portion pi into d, 2 pi r into d, right? So this is the length of the conductor. So simply this is F is equal to B into I into L in the form. So this is how the final force, radial force on the transformer windings can be calculated. Now tangential force acting on tangential component of radial forces. Now these radial forces acting on the windings, what they will do? They will, since they will be acting uniformly throughout the circumference of the winding, so they will cause actually a tension in the conductors. Tension in the conductors. Now, what is this tension? Tension, or what is this tangential force? This is actually tangential force. So, how to calculate the tangential force? Let us divide this winding into two halves. This is the line by which let us divide this into two halves. This one, this circular ring. Assume this as a circular ring, and then divide into two parts. Now, consider this point as well as this point. Here, so equal and opposite forces must be acting here, tangential force. So, total tangential force you can calculate here, if you can calculate these two. So, those two must be equal and opposite here, the tangential force, right? Now, total tangential force acting on these 2 points. So, you can integrate, for example, consider at any position. This is dFr. So, the force that is acting within this d theta. So, at theta, consider at a theta position, and then small width you assume. In this small width, whatever force is acting is dFr. Total force is Fr. In the small width d theta, dFr. And this dFr, you can divide it into components. This is dFr cos theta. dFr cos theta. This is this component is dFr sin theta, which is actually contributing to tangential force here. Right. So, total such tangential force from this angle, from 0, this is 0 position, to pi, from for this position it is pi. So, until 0 to pi, total tangential force, if you find it out, that will be, this is 2 times, this is one tangential force, this is another tangential force, because you have only these 2 points which are common to this entire, this half, semicircle, half circle. So, here those two forces will be reflecting. So, and you have for this rest of the half portion of this circle, again that you can find out 2 forces like this. These 2 forces will be balancing these 2 forces, equal and opposite. So, this is the tangential force that is acting on that. So, if Fr is the radial force acting on the full winding, then the radial force acting on the segment is dFr is equal to, this dFr is equal to Fr divided by 2 pi, because Fr is total radial force acting on this ring, you can say. So, Fr divided by 2 pi into d theta, this small angle d theta, is the value of dFr. Now, thus the total tangential force can be obtained as, so here Ft plus Ft. So, 2Ft are same as this thing, 2Ft equals to 0 to pi dFr sin theta d theta. So, if you solve it, you will get Ft is equal to Fr by 2 pi. This is the tangential force in the windings. So, this is total tangential force again. But winding has several number of turns, and then each turn has A as its cross-sectional area. If you take it, the tangential force per turn, per unit area, unit cross-sectional area of a winding conductor for a winding with the total n turns and the conductor cross-sectional area A denoted by small ft is given by small ft is equal to Fr divided by 2 pi n into A. So this is newtons per meter square, because A is in area, A is in meter square if you assume. So this is how small ft, the tangential force acting on the conductors. Substituting the obtained expression for radial force from equation 2 in the above equation, we obtain tangential force F of t is equal to this. The radial force we have just found out now, that if you substitute here, you will get this equation, and upon simplification, it will come to this area, to n pi d by a into 10 to the power of minus 7 into I square by hr. Now here one interesting this thing, if you divide and multiply by resistivity rho and replace this quantity rho into length by area by r, resistance r, you will get simply f of t is equal to 10 to the power of minus 7 by rho hr into I square r. This is called Hooke's tension actually. So thus the tangential force is proportional to ohmic laws. Actually it is not ohmic, it is this resistivity term is there here. Of course, if the material is same in the design, you can take resistivity is also constant. Therefore, this entire thing is some constant into I square r. So I square r, so it is proportional to I square r. So the rating, current rating of the winding, and r is the resistance of the winding. So this is how the tension force within the winding conductors can be estimated. Tangential force and axial forces. Now the axial forces tend to bend the conductors in the axial direction, and their sum total acts on the coil clamping ring and other clamping structures. So the nature of these forces is such that they tend to cause a contraction or expansion, thereby, if allowed to act independently, cause a change in the height of the windings, which is also reflected in the Rogowski height also. Therefore, we can differentiate with Rogowski height also. The axial forces are unequally distributed between the inner and outer winding. They are not equally distributed. The highest axial forces are experienced by the outer layers of the winding, because you can see the radial component of the flux will be at the outer portions of the winding. Then the axial forces, to calculate axial forces, we have to differentiate the same energy expression with respect to Rogowski height HR. Thus the total force FA, FA1 plus FA2 means, here this is FA1, this is FA2, FA1 plus FA2, similarly at the bottom also FA1, FA2. So the total axial force is FA is equal to FA1 plus FA2, which is obtained by differentiating energy with respect to HR, the Rogowski height. So if you differentiate, minus half mu naught n square I square by HR square pi d into W1 by 3 plus W2 by 3 plus Wg. This is the total axial force. Now, an alternate way to calculate the axial force is to treat the radial flux density separately, to use the physical winding instead of the Rogowski height. Now, if Br denotes the radial flux density, Ni, the total current for the height h, so Ni by h is the ampere turns per unit length into dx is the ampere turns per dx length. Then the axial force acting on the winding between any 2 points A and B. You can see here, this is the dx length. Okay, this is a distance x, and A and B are indicated here. So the total axial force acting on the winding between any 2 points is FAB, is the integration of A to B, BIL concept here. BR into Ni by H into dx into pi d equals to Ni by H is a constant that can be taken out, and integration of Br pi d dx. If you simplify this one, it is flux density only, flux only. Flux density into area will give you flux only. So Ni by H into flux at position B minus flux at position A. So this can be further simplified. We know that phi is equal to phi m cos omega t, and phi RMS is equal to phi m by root 2. And therefore E equals to n d phi by dt by n equals to minus omega phi m sin omega t, or E RMS is equal to phi RMS by omega is equal to E, let us say. Thus, FAB is Ni by H into EB by omega minus EA by omega, neglecting the voltage drop in the windings. If V denotes the RMS value of the supply voltage, thus we have FAB is simply Ni by H omega V of B minus V of A. So this is, now you can see Ni into VB minus VA. V into I, this is apparent power. Axial force is therefore proportional to apparent power. So this is how the forces acting in the transformer can be calculated.